Welcome to another podcast. In this episode, we're going to be taking a look at a short introduction to polar coordinates. Specifically, I'm going to look at the change of variable formulas for polar coordinates and talk about some of the inconsistencies with how we denote polar coordinates, as well as make sure that you understand kind of graphically what these things are going to look like. Starting out with, I want to talk about the differences or the distinctions between Cartesian or rectangular coordinates versus polar coordinates, and the easiest way to do this is by plotting some points. So I'm going to look at the point A and B for the y, so this is on the x, y plane, so our typical what we would call Cartesian coordinates, so this denotes the point AB, and we've got links A and B here, but there are other ways. So this would be the rectangular form, since this forms a rectangle to get to that point. This is the rectangular form, or rectangular way of locating points in the coordinate plane. It turns out that there is a easier, not easier, but another method that can describe the same point, and that is consider having a radius that you swipe through that has an angle theta, and you can alter the length of that radius. If you look at what I'm doing here, I can adjust to any point by altering my radius and my angle anywhere I want to go. So if I want to go to the point AB, that's how I would reach it. And the way to describe how to reach that point is you're giving two parameters. One parameter is the angle theta that you rotated to get there. The other one is the length of the axis that it takes to get to that point, which we would call the radius to that point. Now, because we're aware of how circles work, then I think of the point AB as lying on a circle of radius r. And so this would be the point R, and then I would go up here to the y-axis. It would intersect at the radius r as well. And if that point AB lies on a circle, then we have descriptions for both A and B in terms of r and theta, and those descriptions are the definition of the trigonometric functions. So for example, I know for a fact here that A is our cosine theta, B is our sine theta, which is another way of saying cosine of theta is A divided by R, where A is the adjacent and R is the hypotenuse, and then sine of theta is B over R, and this is where B is the opposite side and R is the hypotenuse. So we understand these relationships very well. And the point is that the x-coordinate then is always going to be described by an r cosine theta. The y-coordinate is always going to be described by an r sine theta. So this is the first change of variable formula. The reason that it's a change of variable formula is if you tell me what theta is, and if you tell me what r is, then I can tell you the x and the y coordinate that correspond to those. Now, typically we'll know x, y though, and we'll want to find r and theta. So we need to have sort of a reverse formula, and the reverse formula comes from looking at the triangle once again. Because r is the hypotenuse of that triangle, then we can immediately say that a squared plus b squared, we can immediately say that a squared plus b squared equals r squared. This is by the Pythagorean theorem. And we also know that if we look at the tangent of theta is b over a. So it's the opposite over the adjacent, which is akin to saying that theta is the arctangent or tangent inverse of b over a. So if you put all that together, that says then that x squared plus y squared equals r squared, and tangent inverse of y over x is theta. This is another way to relate x, y, r, and theta. So this relationship would involve giving or knowing x and y. And if you know x and y, notice you can plug them into both parts here and end up finding r and theta as a result. So this first formula is a way to convert from r theta to xy. That's what the first boxed formula is. The second boxed formula is a way to convert from xy to r theta. And it turns out that this direction, xy to r theta, is the one we have to be careful. I'm going to look at a couple of examples of this. First example here is I want us to convert, let's start with the easy one first. I want us to convert the point r theta equals 2 pi thirds. I want to convert that to a description of that point in the xy sense. So if we just give a small sketch of this, our radius is 2, our angle is pi thirds. So there's pi thirds. And the radius is 2. So in the r theta plane, this is the point 2 pi thirds. Once again, our angle theta is going to be in terms of radians here. Okay, if I want to describe that in terms of x and y, then I'm using the first boxed formula. X would be equal to r, which is 2, cosine of pi thirds. Y equals to sine of pi thirds. And if you know your pi thirds angles, cosine of pi thirds is 1/2, so this is 2 times 1/2, or 1. And sine of pi thirds is square root of 3 over 2, so this is 2 square root of 3 over 2, which is square root of 3. So the point xy for this particular example would be the point 1 square root 3. So this is 1 and this is square root of 3. So that's an alternate way of describing that point. All right, let's look at a slightly harder one here, and that is going in the opposite direction. If we were to go in the opposite direction, a good one to look at would be, let's look at the point, let's see, xy equals 2, -1, and I want to convert this to polar coordinates r and theta. Once again, I want to look at a picture. So the picture here is going to involve us having this point. So we're at -1 and 2. So we are looking at this point, which would involve this angle right here and an unknown radius. So I need to find the angle and the radius in this case. Well, using the second boxed formula, we know that the radius is equal to the square root of x squared plus y squared. That's the square root of 4 plus 1, or the square root of 5. So I know immediately that the length of this curve, or the length of this radial element, is square root of 5. All right, what about the angle? Well, theta is the tangent inverse then of -1/2. And in radians, if you plug this into a calculator, in radians you're going to get -0.463 radians, or you're going to get -26.57 degrees, depending on which mode your calculator's in. And that seems to make sense given the picture. It looks like this angle theta could indeed be 26.57 degrees, or -0.463 rad. Here's the issue, though. That's just one way to interpret this problem. What if I wanted to interpret it differently by looking at the following? So here I've got the point, let's see, at 2, -1, and rather than take and draw the point by rotating from here down to here, What if I went the other direction? What if I went all the way around to here? Then the idea at that point would be very different. We would have an angle theta, which goes all the way around. So an angle theta which goes all the way around, and theta would be 360 degrees minus 26.57 in this case, which turns out to be 333.4 degrees. So I have two descriptions now. The description from above is that r is square root of 5 and theta is negative 26.57 degrees. The description for this picture is square root of 5, but theta is positive 333.4 degrees. So the question is, which one is correct? The answer is they both are. This is one of the unfortunate things about polar coordinates is polar coordinate representations are not unique. So the only way that we can make this unique is if we agree to giving or reporting coordinates in a very, very particular way. There's two possible methods. Let me describe what the two possible methods are. The first is I can think of rotating only from 0 to 2 pi. The second possible way is I consider rotating from minus pi to 0, 0 to pi, so it would be in total minus pi to pi. Both of those are possibilities. It just depends. You have to read books carefully that involve polar coordinates because you have to know which of those two conventions you're using. For our purposes, we're going to state that when you report the coordinates of a point in terms of polar coordinates, that there are two things that must be true. R has to be greater than or equal to 0, so I don't want to look at negative radiuses. Negative radius would be if I rotated this curve to here. So I rotated around to here and I looked at the angle going in the opposite direction. So if my angle of rotation was to here and then it was negative, so it would get back to here. That's very tricky. It turns out that in that case that would be negative root 5 and the angle here would be 153.43 degrees in that case. So all three of these are correct. But the one that we want to use is the one that I started with, the one in blue, because I want my radius to be positive. I don't want to give negative radiuses or radii. And the angles that I want to look at have to come from the interval from minus pi to pi. So I don't want large values, and I need to enclose pi there. Since negative pi and pi are the same angle, I'm going to choose the positive one if it happens to be pi. But that's just a very, it's what's called a convention. It's something that we've all agreed to do. And so if you report any polar coordinates that you work with in terms of a positive radius and a theta value between minus pi to pi, then it'll make things go more smoothly. So this is just a way to convert between XY coordinates and polar coordinates. It's a soft introduction. I hope you've seen this before prior to being in this class, but if you haven't, read up more about it in the textbook. I do want to take one quick second and show you some of the beautiful graphs that you can get out of this. I took the time to look at these in Maple. And so here's an example of the graph of r equals sine of 8/5 theta. When I think of polar curves, I think back to when I was a kid and you had these things called spirographs, which were these sort of cogwheel looking things that you'd stick the pencil in the middle of it, and then you would run it around the paper, and it would make these sort of circular pictures very similar to this. That's what polar coordinates are, because moving your pen around involved a rotation, and then the wheels were designed in such a way that they would vary the radius as you ran your pen around on the paper. And so this is one such picture that you could get. Another one here is the graph of r equals 1 minus cosine theta. This particular graph is this little heart shape here. It may not seem like much, but this is a very important shape. This is called a cardioid, and in fact the microphone that I'm speaking into right now is a cardioid mic, which means that it picks up sound. So the mic is placed at the epicenter here at 0, and the mic picks up sound in front of it, but it also picks up sound slightly behind and to the right of it, and then there's a dead spot directly behind it. So this talks about the sound pickup region for a cardioid mic. So it's actually a very important figure to be able to understand, and it's expressed as 1 minus cosine theta in terms of polar coordinates. So we might want to know what is the total area picked up by the mic, which is something we're going to talk about in class. So here's a example of several different curves. I wanted to show you that also when you talk about polar coordinates, circles are sort of right around the corner. So what I've done here is I've graphed the circle by just graphing r equal to 2. So a circle is defined by just giving me a radius in polar coordinates. So this green curve here on the outer edge is just the polar curve r equal to 2. The blue curve here is a little bit different. This is the curve 2 sine theta. So we've moved things up a little bit and we've shrunk the radius by 1. But that is if you have 2 times sine theta or 2 times cosine theta. 2 times cosine theta is the red circle here. Then those are circles. If you multiply 2 by a value, 3 by a value, whatever, those are going to create circles. And then I've got the negative versions of them over here. So circles are very simply described in polar coordinates, as we're going to look and verify certain formulas for those in class. So I just wanted to give you a little bit of a glimpse at the kinds of figures that you can create using polar coordinates, and more importantly, getting back to where we discussed polar coordinates here, we're talking about the importance of correctly identifying the polar coordinate that you're working with, and then the conversion formulas that we talked about. All right, thank you for watching.